So now we will be talking about one more topic in convex optimization, which is strongly convex functions. So earlier we have read about convex functions and strictly convex functions. So if a strict inequality is followed in the definitions of convex functions or in the first and second order convex functions, then it's called as strictly convex functions. Now we have one more type of convex function which is termed as strongly convex function. So let's see what it means. So if f is a function from Rn to R, which means it's a function which maps vector in n dimension to a real number, and this function is M strongly convex, and note that the parameter M is greater than 0. If f of x, that is the function value at x minus m by 2 times norm of x squared, is convex, and m is called the strong convexity parameter. So let's see what this M is and how this M affects the convexity of a function, and what are its implications. So we have a remark that we need to note. If f is twice continuously differentiable, so if f is a function which is 2 times so it's differentiable and its derivative is continuous, and this is for 2 of its derivatives, then f is M strongly convex if and only if, so this is implies and is implied by condition, if and only if my Hessian of f at x is greater or equal to m times I, where I is the identity matrix. And this follows from the second order condition for convexity. Let g of x be f of x minus, so I get this from here, m by 2 norm of x squared, then my del square g of x would be greater or equal to 0, and from this I'll get del squared of f of x minus m times I is greater or equal to 0. So from the definition of M strongly convex function, we have this thing, and when we do double differentiation of this, we get this condition. Now we have a proposition which follows. The proposition states that the following statements are equivalent. So what are the statements? The first statement is that f is a function, and this function is continuously differentiable, and it's M strongly convex. The second condition is that f is continuously differentiable and this thing is true, that is f of alpha x plus 1 minus alpha y is less or equal to alpha times f of x plus 1 minus alpha times f of y. Now this condition is true for any convex function, but the additional thing for M convexity is that we have one more thing, which is minus m by 2 alpha 1 minus alpha times the norm of y minus x squared for alpha belongs to 0 to 1. And then we have a third implication, which is that my function f of y is greater or equal to f at x plus del transpose f at x times y minus x. So we also knew this condition from the definition of convex functions, but if it's m strongly convex, then we have additional term, which is plus m by 2 times norm of y minus x squared. And then the last proposition is that if I take del of f of y and subtract it by del f of x and take the transpose, this quantity times y minus x would be always greater or equal to m times y minus x squared. So these are the four implications, and this follows from the definition of M strongly convex functions. So let's move on to the proofs. So how we will proceed is, so we are saying that all these conditions are equivalent, which means that if first condition is true, it will imply that second condition is true. If second condition is true, it will imply that the third condition is true. If third condition is true, it will imply that the fourth condition is true. And similarly, if the fourth condition is true, it will mean that the first condition is true. And so the implication will follow. So let's see how it works. So we have to show that the proposition A implies and is implied by proposition B. Then we will show it proposition B implies and is implied by proposition C. Proposition C implies and is implied by proposition D. And finally, proposition D implies proposition B. So this is how it will follow. So let's first move on to the first part, which is we'll show that A implies and is implied by B. So what is A and B? Let's see. So A states that f is continuously differentiable and M strongly convex. So we can take this as our assumption and prove the second condition, which is that if this is true, then f of alpha x plus 1 minus alpha times y is less or equal to alpha times f of x plus 1 minus alpha times f of y minus m by 2 alpha times 1 minus alpha times 2 norm of y minus x whole power 2. So this additional m term will follow from the definition of M strongly convex functions. So let's see how we can proceed. So we say that g of x is equal to f of x. We stated this in the definition of M strongly convex functions. So g of x is equal to f of x minus m by 2 norm of x ka whole squared, and we are given that this is convex because the first proposition states that f is continuously differentiable and it is M strongly convex. So the function is convex. Now what we can do is we can write it like this. So we have alpha x plus 1 minus alpha times y. If we look at this thing, this should be less or equal to alpha times g of x plus 1 minus alpha times g of y. How does this come? From the definition of a function being convex. So if a function is convex, then this condition is true. Now, from the definition of g of x, we can put x equals to this whole thing and use it over here. So I'll have f of alpha x plus 1 minus alpha y minus m by 2. Instead of x, I'll write alpha x plus 1 minus alpha y whole squared, and this quantity should be less than or equal to alpha times f of x minus m by 2 times 2 norm of x squared. So how does this come? So from this definition, this is less or equal to alpha. So alpha is here times g of x. So g of x is this quantity plus 1 minus alpha times g of y. So instead of x in this function, I'll just put y. So I'll have f of y minus m by 2 times the 2 norm of y whole square. So let's move on and solve it further. So I'll have f of alpha x plus 1 minus alpha times y is less or equal to, I can shift this thing to the right. So it will be less or equal to alpha times f of x plus 1 minus alpha times f of y plus m by 2 norm of alpha x plus 1 minus alpha y whole square minus alpha by 2m norm of x. Sorry. So this comes when we simplify these expressions. Minus 1 minus alpha times m by 2 times norm of y squared. So this is equal to alpha times f of x plus 1 minus alpha times f of y minus m by 2 alpha times 1 minus alpha norm of y minus x squared. So we have proved the first part. We have implied from the first thing that if first part is true, then it implies second part. So how we proceeded from the second last step to the last step is that we simply simplified the expression that we already had, and we got the final conclusion. Now let's move to the next part, which is we'll show that B implies C. So for this, I'll say that my function f of alpha x plus 1 minus alpha y is less or equal to alpha times f of x plus 1 minus alpha times f of y minus m by 2 alpha 1 minus alpha norm of y minus x whole squared. So where from this thing came? This thing came from part B, because part B says that this is true if the function is convex. Now how can we imply the third condition, which is that f of y is greater or equal to f of x plus del transpose f of x y minus x plus m by 2 y minus x whole squared. So let's see how we can come to that conclusion. From this thing we can write, we have f of x plus 1 minus alpha y minus x minus f of x is less or equal to 1 minus alpha f of y minus f of x minus m by 2 alpha into 1 minus alpha times norm of y minus x whole squared. Now we can write that f of x plus 1 minus alpha times y minus x minus f of x upon 1 minus alpha is less or equal to f of y minus f of x minus m by 2 alpha y minus x whole square. So I have simply put 1 minus alpha to the left, and for this thing how I came over here is that I have taken x separately. So what I have done is I have added and subtracted x, and the rest of the term is same, and minus f of x comes from the right hand side is less or equal to 1 minus alpha f of y minus f of x. So on the right hand side as well I have added and subtracted, so plus minus f of x I have done. The plus term goes to the left and becomes minus, and the minus term will be compensated over here. So what we have done is we have added and subtracted f of x from both sides, and then we have our condition m minus m by 2 alpha 1 minus x and y minus x whole square. This is the same. Now how we proceeded from this step to this step. So what I have done is I have 1 minus alpha common on both sides. So what I did, I have taken it as common and divided the left hand side by this quantity 1 minus alpha. So this whole thing will be lesser than or equal to the thing that will be remaining on the right hand side is f of y minus f of x minus m by 2 alpha y minus x whole square. I hope the theorem proof is clear till this point. Next what we will do is we will take limit alpha goes to 1 on both sides. So if we take this limit, the left hand side, this which is this whole thing, will become the gradient, right? So it will be the gradient of f at x transpose times y minus x, and this quantity is less than or equal to f of y minus f of x minus m by 2 norm of y minus x. So this takes place when alpha goes to 1. So this quantity will also go to 1, and when this goes to 1, this whole thing will go to 0 and this whole quantity will go to infinity. So we'll have the definition of derivative, which is the gradient. So gradient of f at x transpose y minus x is basically equal to this. So let's proceed further. So from this condition I can say that f of y, which is over here, is greater or equal to f of x plus del f of x transpose y minus x plus m by 2 y minus x whole squared. So we have proved our third implication as well. So we have assumed that B is true, and from that we showed that C is also true. Let's move on to the next part, which is that we have been given C, and we have to show that C implies D. So what is C? C is this statement, and from this I have to prove D, which is this statement. So let's get started. So I'll have from my third condition that f of y is greater or equal to f of x plus del transpose f of x y minus x plus m by 2 y minus x whole squared. Now I can call this inequality as inequality number 1. So I am basically naming the inequalities, and then I can say that instead of y I'll put x. So I'll have f of x is greater than or equal to f of y plus del f of y So what I have done is I have replaced x by y and y by x, and of course this inequality still holds. Now I will add 1 and 2. So if I add 1 and 2, what I'll see is that I'll have f of y plus f of x on the left hand side, and on the immediate right I'll have f of x plus f of y. So both these quantities would get cancelled and I will have a net 0 on the left hand side, and this should be greater than or equal to. So on the right hand side I will have del of f of x minus del of f of y transpose times y minus x. So you can solve this thing, and you will see that you will get this plus m. So m is my m strongly convex parameter times norm of y minus x whole square. So this implies that f of del of f of y minus del of f of x transpose y minus x is greater than or equal to m times y minus x whole squared. So this is what we had to prove in our third part. So now we are not done yet. We have to still show one more thing, which is that I have to show that D also implies B. So which means that if this thing is true, then what else will be true? Then this thing will also be true. So from this I have to imply this. So let's see how we can do that. So I will let parameter z be equal to alpha x plus 1 minus alpha times y, and we have that g1 of t is equal to f of x plus t z minus x, and my g2 of t will be f of y minus t z minus y. So from D I have to imply B. So from first fundamental theorem of calculus we have that g1 of 1. So if I put t equals to 1, I'll get this is equal to f of this is equal to g1 of 0 plus integral 0 to 1 g1 dash of t dt. Now I will use the value of the function g. So when t is equal to 1, this quantity will be f of z. So I'll have f of z is equal to f of x, because it will get g of t equals to f of x when t is equal to 0 plus integral from 0 to 1 del f of x plus t z minus x transpose z minus x dt. So let's call this as equation 3. Now we will again apply FTC on g2 function. So I'll have g2 of 1 is equal to g2 of 0 plus integral 0 to 1 g2 dash of t dt. So from this I'll have one more condition, that f of z is equal to f of phi plus integral 0 to 1 del f of y plus t z minus phi whole transpose times z minus phi dt, and this we'll call as equation 4. Now what I will do is I'll multiply equation 3 with alpha and I will add them both with 1 minus alpha times equation 4. So let's do it. So this is our 3 and this is our 4, and if we multiply this by alpha and this by 1 minus alpha, we add them together, what we will get is, so we have alpha times f of z plus 1 minus alpha times f of z is equals to f of alpha times f of x plus 1 minus alpha times f of y, and then I'll add alpha into 1 minus alpha integral from 0 to 1 del of f x plus t z minus x minus del f y plus t z minus y transpose y minus x dt. So what I have done is I have simply multiplied the third equation with alpha and the fourth equation by 1 minus alpha, and then I have added both the equations. Now I can say that my right hand side is actually equals to alpha times f of x plus 1 minus alpha times f of y plus, now let's look at this. So I have alpha 1 minus alpha, then I have integral from 0 to 1, and then I have del of f at x plus t z minus x minus del f y plus t into z minus y transpose times x cap minus x bar upon 1 minus t dt. So now this condition we have got from the upper thing. So what I can do is I can do some assumptions. The first assumption that I'll do is I'll assume that this function is equals to x cap, and this function equals to, this function is x bar and this function is x cap, and so what I'll be left with is x cap minus x star. So let's proceed. So this whole quantity is greater than or equal to alpha times f of x plus 1 minus alpha times f of y minus alpha into 1 minus alpha integral 0 to 1 m times x bar 1 times x cap minus x bar upon 1 minus t dt. This is equal to alpha f of x so we have come to this point that we have this whole quantity is greater than or equal to this, times 1 minus alpha times this minus alpha 1 minus alpha integral from 0 to 1 m of norm x star minus x bar whole square. So this is actually cap dt divided by 1 minus t. So I'll have alpha times f of x plus 1 minus alpha times f of y minus alpha times 1 minus alpha so what I'll be left with is alpha times 1 minus alpha m integral from 0 to 1 norm of 1 minus t times 1 minus x whole squared upon 1 minus t dt. This is less than or equal to alpha f of x plus 1 minus alpha f of y minus alpha into 1 minus alpha is less or equal to alpha times f of x plus 1 minus alpha times f of y minus alpha times 1 minus alpha m times y minus x का whole squared integral 0 to 1 minus t dt, and if you apply the integral over this, I'll simply get it to be equal to 1 by 2. So I can further simplify this theorem by stating that this is equal to alpha times f of x plus 1 minus alpha times f of y minus alpha times 1 minus alpha m by 2 times modulus of y minus x whole square. This is actually norm of y minus x whole squared. So what I have proved is, I have proved this thing that my norm of xk minus x star whole square is less or equal to 1 minus m by 2l whole square raised to power k. So this is how we proved it.